Mathematics is all around us and it is something that we could not neglect no matter what. Good day everyone, we are Group 7 and today we will be talking about exponential concepts. But before we commence, allow me to introduce the people behind this video tutorial. There are 5 teacher reporters for this video tutorial, and first is Miss Cindy S. Tanyak. She is a licensed professional realtor over 7 years of experience in financial management. She graduated with bachelor's degree in finance and accounting in Silliman University. She is also on the go in guiding and assisting sellers and buyers in purchasing properties. She is the CEO of the famous and big-time clothes and sneakers company, Flair. The next one is Miss Sheena Rose A. Magalso. She is a summa cum laude and a graduate from the University of the Philippines. She is also the New York Times best-selling author of 35 books and has received numerous honors, including the Elizabeth P. Ritchie Distinguished Professor Award, Coretta Scott King Author Honor, the 2014 Distinguished Teaching Award, and was labeled as UP's Eminent Professor. She is currently teaching at Harvard University, and many people admire her for her ability to make advanced mathematics understandable and pleasant. She also continuously encourages curiosity and excitement, and she has a gift for timing and precision, precisely asking the perfect questions to encourage students to consider the implications of their argument. The third one is Miss Ara Angelique C. Saluan. She is a cum laude graduate from the Pangasinan State University. She finished her Master of Arts in Mathematics Education at the University of the Philippines in 2015. In 2018, she obtained her PhD Math Ed from the same institution. From 2014 to the present, Ms. Saluan is a math teacher at LaSalle Green Hills. She is also a member of the following organization: Philippine Council of Mathematics Educators, Mathematics Teachers Association of the Philippines, and Mathematics Trainers Guild. The fourth one is Ms. Jasmine Seden P. Sarancio. She is a calculus professor at University of San Carlos and a businesswoman at 127 Incorporated, where backpacks are made from plastic materials. She finished her Master of Arts in Mathematics Education at Silliman University last 2014. Also, her business started off as a small and local business after she graduated and now has a company to run in the span of 5 years. As a teacher and a businesswoman, she holds business meetings to represent her company all over the world to help alleviate plastic waste worldwide. The last one is Mr. Felipe Gabriel J. Diago. He holds the degree Bachelor of Secondary Education major in Mathematics from the University of the Philippines in 2015. His undergraduate research focused on the diagnostic assessment of grade 7 students as a basis for individualized intervention program. He is currently working on his academic units for the degree Master of Arts in Education with specialization in Mathematics Education from the same institution. He is currently the high school mathematics teacher of Maria Montessori Founding, teaching Math 7, 8, 9, and 10. Now let us proceed to exponential equations. But before anything else, let us first define what are exponential equations. Exponential equations are equations in which variables occur as exponents. For example, exponential equations are in the form a raised to x is equal to b raised to y. To solve exponential equations with same base, use the property of equality of exponential functions. If b is a positive number other than 1, then b raised to x is equal to b raised to y if and only if x is equal to y. In other words, if the bases are the same, then the exponents must be equal. At this juncture, let us talk about the types of exponential equations. There are 3 types of exponential equations, and they are as follows. First, equations with the same bases on both sides. Example, 4 raised to x is equal to 4 raised to 2. Second, equations with different bases can be made the same. Example, 4 raised to x is equal to 16, which can also be written as 4 raised to x is equal to 4 raised to 2. And lastly, equations with different bases that cannot be made the same. Example, 4 raised to x is equal to 15. We all know that 4 is divisible by 2 and 4, while 15 is divisible by 3 and 5. Now let us have a recap about the laws of exponents. First, we have x raised to m times x raised to n is equal to x raised to m plus n. Then the second one, we have a power of a power rule. And that is x raised to m raised to n is equal to x raised to m times n. The third one is a power of a product rule. We have x times y raised to n that is equal to x raised to n times y raised to n. The fourth one is the division rule. That is x raised to m over x raised to n is equal to x raised to m minus n, and x should not be equal to 0. Also, we have the power of quotient rule wherein x over y raised to n is equal to x raised to n over y raised to n, and we must always remember that y should not be equal to 0. The sixth one is what we call the zero exponent. We all know that any number raised to 0 is always 1. The seventh one is what we call the negative exponent. So we have x raised to negative 1, and that is equal to 1 over x. The last one is x raised to m over n, and that is equal to the n root of x raised to m. Now, at this point, I will be the first one to give you an example about exponential equations, and that will be followed by my group mates, Sedin, Cindy, Ara, and Felipe. So the first example is 2 raised to 3 minus x is equal to 4 raised to 2 minus x. The first thing that we are going to do is to write the expression in exponential form, with a base of 2 of course. And with that, we have 2 raised to 3 minus x is equal to 2 raised to 4 minus 2x. Since the bases are now the same, we must set the exponents equal, and that will be 3 minus x is equal to 4 minus 2x. The next thing that we are going to do is to move the variable to the left side while changing its sign because it passes through the equal sign. We will also move the constant to the right side while also changing it from positive 3 to negative 3. Then we are going to combine like terms and subtract the numbers. So 4 minus 3 is equal to 1. So our final answer is x is equal to positive 1. Now, let us do the checking to make sure that our answer, which is positive 1, is correct. So, once again, our equation is 2 raised to 3 minus x is equal to 4 raised to 2 minus x. And at this juncture, we will now be substituting our answer to all of the x found in our equation. And that will be 2 raised to 3 minus 1 is equal to 4 raised to 2 minus 1. The next step is we will going to subtract the exponents. Then, we are going to evaluate the power, which is 2 raised to 2 will now be 4, and any number raised to the power of 1 equals itself. This is true because both sides are identical. So now, we have proven that our answer, which is positive 1, is correct.
First, we write the equation, which is 8 to the power of negative x equal to 2 to the power of x minus 8. To solve this, we have to make sure that both of their bases have the same, so we have 2. 8 is equal to 2 to the power of 3. That is why we need to write 2 to the power of negative 3x. Then, we copy the other term, which is 2 to the power of x minus 8. After this, let's copy their exponents. So we have negative 3x equal to x minus 8. Then, let's combine like terms. Negative 3x minus x equals negative 8. So it becomes negative 4x equals negative 8. To find the value of x, let's divide both sides by negative 4. Therefore, our final answer is x equals 2. Now let's check. First, we copy the original equation, which is 8 to the power of negative x equal to 2 to the power of x minus 8. Then, we'll substitute x with its value, which is 2. Therefore, we have 2 to the power of negative 6 equal to 2 to the power of 2 negative 8. Let's copy the exponents, which are negative 6 and 2 negative 8. After simplifying, we get Negative 6 equal to negative 6. Since both sides are equal, therefore the equation is true.
The next equation that we're going to solve is 4x equals 2 raised to the power of x plus 1. We all know that 4 is a perfect square which can be written as 2 squared. And as we can see in the equation, there is an x. And so, copy x equals 2 raised to the power of x plus 1. Substituting 4 as 2 squared. Are they having the same base? Yes, they are. Therefore, we can equate exponents equals x plus 1. Now, we're going to transfer x to the left. So from positive x, it becomes negative x. Minus x equals 1. Since there is a visible 1 before x, we can subtract 2x with x, which is the result. X equals 1. That is your final answer. If you are unsure of your solution, we can check if it is true or not. Check or checking. For x equals 2 raised to the power of x plus 1. The answer of our solution was 1. Therefore, we're going to substitute the x with 1. 4 raised to the power of 1 equals 2 raised to the power of 1 plus 1. 4 times 1 is 4 equals 2 raised to the power of 1 plus 1 is 2. And so the square root of 4 is 2. Therefore, 2 raised to the power of 2 is 4. And now you can see that the result and your answer is true.
For this equation, we have 5 raised to the power of 3x plus 2 equals 25 to the power of x minus 1. Our bases are 5 and 25. Now we cannot transform 5 into another exponential figure because this is already in its simplest form. As for 25, it is a perfect square which can be written as 5 squared. So we can just directly bring down the left side. 5 raised to the power of 3x plus 2 equals. Now from 25, this turns into 5 squared raised to the power of x minus 1. Now we have to multiply our exponents, distributing 2 to every term of our second function. So now we have 2x minus 2. Since we both now have the same base, therefore we can equate exponents. Bring down our exponents, 3x plus 2 equals 2x minus 2. Now we're going to transpose 2x to the other side, making it negative 2x. We will also be transposing 2 to the other side, making it negative 2. We can now combine like terms. 3x minus 2x, we get 1x or x. Bringing down the right side, negative 2 minus 2. Now we can solve for negative 2 minus 2. And this gives us negative 4. This will be our final answer. Now to check, we must write our original equation. Five raised to the power of 3x plus 2 equals 25 to the power of x minus 1. Now we substitute our x, which is 4, to every x in the equation, making it 5 cubed to the power of negative 4 plus 2 equals 25 to the power of negative 4 minus 1. Since both our bases are not the same, we must transform 25 into another exponential figure, bringing down 5 cubed to the power of negative 4 plus 2 equals 25, which will be now turned into 5 squared. We then place its exponent, negative 5, which is the product of negative 4 and negative 1. Since we both have the same base, we can now equate exponents, bringing down 3 times negative 4 plus 2 equals 2 times negative 5. Three times negative 4, we get negative 12, bringing down positive 2. We will also be bringing down the right side, 2 times negative 5. Finally, we combine negative 2 plus 10, which will give us negative 10. In the other side, 2 times negative 5 will also give us negative 10. Since both sides are equal, therefore, the equation is true.
First, we're going to write the equation. Three to the power of 2x equal to 9. To solve this, both places have 3 because 9 is divisible by 3. 9 is equals to 3 to the power of 2x, that is why we need to write 3 to the power of 2x, then we copy the other term which is 3 to the power of 2. Now, copy the exponent for both sides. So we have 2x equals to 2. To get the value of x, we have to divide both sides by 2. Therefore, cancel 2 and 2 divided 2 is equals to 1. So therefore the answer is x equals 1. Let's check. Copy the original equation, which is 3 to the power of 2x equals to 9. Substitute the value of x with its value. We have 3 to the power of 2 times 1 equals 9, equals to 9. Also, 3 to the power of 2 times 1 equal to 3 to the power of 2. Let's copy the exponent, which are 2 times 1 equals 2. Let's multiply 2 with 1 equals to 2. So, 2 is equal to 2. Since the equation is equal, therefore it is true.
We are done with exponential equations, so let's move on to exponential inequalities. First, let us define what are exponential inequalities. So exponential inequalities are inequalities in which one or both sides involve a variable exponent. They are useful in situations involving repeated multiplication, especially when being compared to a constant value, such as in the case of interest. We also have 4 properties of exponential inequalities. In the first property, it states that the assumptions, if your base a is greater than 1 and you have an exponential inequality a to the x less than a to the y, then all you have to do is to copy the same inequality symbol, which is less than, and you only have to bring down the exponents. The second property states that if your base a is greater than 1 and this time you have greater than a to the x greater than a to the y, then you can copy your inequality symbol, which is greater than, and you have to bring down the exponents. The third property, on the other hand, states that if your base is less than 1 but is greater than 0, like decimal figures 0.1 to 0.9, or even fraction figures like 1/2, 1/3, 1/4, 3/4, and a to the x is greater than a to the y, then your inequality changes into the opposite direction. So, from greater than, it will become less than, and then you must not also forget to bring down your exponents. And for the fourth property, if your base is less than 1 but is greater than 0, then if you have a to the x less than a to the y, then from less than, it will become greater than, and then you have to bring down the exponents. So basically, for properties 1 and 2, the inequality symbols will not be changed, provided that your base is an element of a number greater than 1. As for properties 3 and 4, the inequality symbols changes into its opposite direction, provided that your base a is less than 1 but is greater than 0. At this juncture, let us proceed to the rules for solving inequalities. So the first one is, if the same real number is added to or subtracted from both sides of an inequality, the sense of the inequality is not changed. The second one states that if both sides of an inequality are multiplied by or divided by the same positive real number, the sense of the inequality is not changed. And lastly, if both sides of an inequality are multiplied by or divided by the same negative real number, the sense of the inequality is changed. Our group will also be providing concrete examples to help you understand this topic even more. So the first example is 4 raised to 4x less than 8 raised to 2x plus 2. The first step that we are going to do is to write it into its exponential form with a base of 2. So that will eventually become 2 raised to 8x less than 2 raised to 6x plus 6. Since the bases are equal and greater than 1, we are going to compare the exponents. Then, we are going to move the variable to the left side and change its sign. And now we are going to combine like terms, and since they have different signs, we are going to subtract, and that will become 2x less than 6. Lastly, we are going to divide both sides of the inequality by 2. Now we have our final answer, which is x less than 3. So our solution for this inequality is x less than 3. Our interval notation is negative infinity and positive 3. And as we can see below, that is the number line. And this is how we are going to plot the inequality using the number line. And for this inequality, it extends to the left.
First, we write the equation, which is 4 to the power of 3x plus 2 less than 64. To solve this, we have to make sure that both of their bases are the same, so we have 4. Let's just copy 4 to the power of 3x plus 2, then rewrite 64 as 4 to the power of 3. After this, let's copy their exponents. So we have 3x plus 2 less than 3. Then let's combine like terms. 3x less than 3 minus 2. So it becomes 3x less than 1. To find the value of x, we divide both sides by 3. Therefore, x is less than 1 over 3. So our solution is x is less than 1 over 3. For decimal, x is less than 0.3333 and so on. The interval notation is negative infinity and 1 over 3. This is how we are going to plot this equation using the number line.
The next equation that we're going to solve is 2 raised to the power of x minus 2 is greater than 8. 2 raised to the power of x minus 2 is already in its base form, meaning to say you cannot transform to another exponential figure with a different base. Therefore, 2 raised to the power of x minus 2 must be retained, and 8 must be transformed into an exponential figure with a base of 2 cubed or 2 raised to the power of 3. So we have here 2 raised to the power of 3. And then we have to bring down the exponents. X minus 2 is greater than 3. The next thing is transform negative 2 to the right. From negative 2 it becomes 3 plus 2. Add 3 plus 2 to get the result x is greater than 5. That is now your final answer. The answer to the solution was x is greater than 5. The interval figure or the interval notation of it is interval notation is 5 to the positive infinity. Moving forward to the number line. Five is already given, therefore you may write 3 as your starting point up until 6. For 5 as the disposition and 6. Since x is greater than 5, the open circle shades to the right.
Here we have an example of an exponential inequality. 2 raised to the power of 4x plus 1, less than or equal to 64. Here our bases are 2. Now 2 is already in its simplest form, so all we have to do is bring down the left side. 2 raised to the power of 4x plus 1. As for 64, this can be written as 2 to the power of 6. Since both bases are now the same, we can now equate exponents. Bringing down exponents, 4x plus 1 less than or equal to 6. Since our bases are greater than 1 and our symbol is less than or equal to, we will use the first property of exponential inequality, which means we no longer have to change its symbol. Now to solve for x, we have to transpose like terms, transposing 1 to the right, turning it into negative 1 to combine with 6. We can now bring down 4x less than or equal to, subtracting 6 minus 1, which gives us 5. To To solve for x, we divide both sides by 4. Which eliminates 4 in the left side. Now we are left with x less than or equal to 5/4. And that is our final answer. Here we write our final solution, which is x less than or equal to 5/4. In decimal form, this becomes x less than or equal to 1.25, which is the decimal form of 5/4. Now in interval figure, since our symbol is less than, then we write down a negative infinity. When using infinity, we must always use a parenthesis. Now we place 5/4, and since our less than symbol has an equality symbol associated with it, then we enclose it with a bracket. As for the number line, this is how we are going to plot our equation. We must first create our number line and writing down 0, 1, 2, and 3. Now to plot 5/4, we place a dot near 1 because 5/4 turned into a decimal is 1.25. We will then place 5/4 underneath the dot. Notice that there is a solid dot above 5/4, which indicates that this is a closed endpoint. In the left, there is an arrow on the end indicating that the answers continue through infinity. And that is all for this equation.
First, copy the original equation, which is 3 to the power of x plus 1 greater than 81. Copy 3 to the power of x plus 1 greater than 3 to the power of 4. We substitute 81 to exponent 3 to the power of 4. Cancel 3, so it becomes x plus 1 greater than 4. Next, x greater than 4 minus 1 equals to greater than 3. for solution, x greater than 3. For interval notation, is open parenthesis 3 comma infinity, then close parenthesis. This is how we are going to plot this inequality using the number line.
Learning exponential concepts is crucial in our daily lives since mathematics is all around us, and we can also use what we've learned and use it to better ourselves and the community. That would be all, and we hope that you learned something from our video tutorial. Thank you very much.